universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, don't touch that dial. This is a live show. Hi, guys. Hi, Tara. How are you?
Hi, Mark. Good to see you.
Likewise.
Good to see everybody.
Good to see. Well, we can't see you, but we hope you're there. Listen, guys. We are in a. This is live tonight, and I'm glad about it because it's been a long time since we've done a live show. Tonight we're going to do something cool. We're going to talk about neutron stars, okay, and we're going to talk about them in a way that is going to make them understandable. When people talk about the words neutron stars, what does that mean? A star made of neutrons, right? Isn't that what you think?
Yeah. Okay. Or a neutron, singing in the universe, singing with the stars type of thing.
Perhaps. Or Jimmy Neutron.
Yes, that too.
But the fact is, like, a neutron is an elementary particle that we find in atoms and floating around in the universe and within stars. But how come we can end up with a star that's composed entirely of neutrons? Well, that's what's coming, and we're going to talk about that. Cool. Then we're going to talk about black holes in a way that's a little different because you're going to get a perspective on black holes that kind of explains why the images we have of black holes, our own and the one in Messier 87, the Virgo galaxy, look the way they do. And that's kind of interesting. But before we get started, I just want to say hello to everybody who's here. We've already got a bunch of people watching. That's great. Good to see you guys. Yeah. And I want to also shout out to Calabos and Tiffany in our Sky Tour family because they are responsible for the equipment giveaways that we'll be doing at Contact in the Desert and the equipment we've given away so far. We are giving away telescopes and binoculars, and we're going to be working toward giving away night vision systems as well from Psionics. And
cool.
That's courtesy of Calabos and Tiffany, and we're going to help out with the night vision systems too. But it's because everybody watching has been great. Tara, the work you've done out in the desert to help us is just unparalleled. I mean, without you and without Marianne going out there, when needed, I would not have this whole 501c3 nonprofit without you guys. You guys are fantastic.
We're a good team, Mark.
Give a shout out to you too, especially.
Yeah.
Okay, yes, that's right. Clap. See, clapping. See, hands going together, making noise.
Bravo, yes, bravo.
I've always thought that that's a weird thing. What do humans do? They bang their hands together to make noise. It's kind of weird, isn't it? I mean, why can't they just go, or bing? Why do they do this? Make noise? Why not this way? Or why not this way? Why not this way? How did this evolve? And it's a whole side note, guys. It has nothing to do with astronomy.
Oh,
it has to do with our evolution, though. Like, why did we evolve? Right? What do you think it is? I mean, do you have any idea?
It's our fins. It's the first thing we did. Our flappers,
Yeah, but why don't we go at the same time then, like seals?
Well, we're usually laughing or talking when we're talking.
That's right. I also want to make note. This is our Sky Tour live stream official shirt, and Tara's actually wearing hers.
I got mine. Yes, I did.
That's right. Oh, yours looks better than mine. It's the same.
I don't know.
We just got new shirts as well, and we'll be making those available to everybody. Plus, they'll be on sale at Contact in the Desert when we're out there.
Can you get them for a donation?
That's right. That's correct. And the price, I think, is $25, but I'm not sure. I mean, do you remember the price? I don't know if you remember the price.
No, Marianne's
she's the pricing guru on that.
She knows the price is right on that one.
Yeah, she does. And her and Drew Carey. So
come on down, everyone. Get a T-shirt.
That's right. So on to the astronomy. One of the things that we like to do here is to, talk about Sky Tour live stream. Obviously, we're showing you the shirts and all that stuff. But what is Sky Tour? Sky Tour is a amazing nighttime live view of the universe that we show you. We show you objects in the night sky, and we talk about them. We tell you their origins, their evolution, where they're going to go, why they look the way they do. And this is something that I have yet to find this online. Oh, yes, you can find videos about what a nebula is and a planetary nebula and a black hole and a neutron star. You can find plenty of videos, but don't you want to see one?
Yeah.
Yeah, I'm going to show you. I'm going to show you a neutron star that we actually took an image of
Oh.
here tonight, and I have it. So, yeah, so that's going to be kind of cool. So I think it's really neat to think about that. And the other thing is, when you look at stellar remnants, the remnants of supernovae, stars that have obliterated themselves in a cosmic catastrophe,
Wow.
cataclysm, where they just spread their guts to the universe again.
Ew.
You, and some of it's red, okay,
Ew.
but it's hydrogen gas, okay, and there's green stuff too, and the green is oxygen. So I mean, yeah, the universe has different
Amazing.
what the colors mean, and
hmm
we'll talk more about that.
It's really
So
cool.
yeah, it is. It is.
hmm
Now, Tara is always someone that has a tremendous number of things to add to anything we talk about, and she will sometimes bring up things I haven't thought of. So it's really wonderful to have her around. So I'm glad you're
Oh,
here.
thank
Thank you.
you.
Yeah, it's really good. So I want to kind of jump into this whole black hole.
Black hole?
I got me.
Jinx, jinx, jinx.
Damn. No, so one of the things that's important to understand, I think, is that when we have a supermassive star, then there's a couple of ways they can go. They can go by exploding in a supernova, and we can explain briefly how that works. That's a whole nother show on how those actually work.
Cool.
And then that explosion can yield, as a result, because of all the intense pressure on that central core of the star, can yield one of two things: either a neutron star of some kind or a black hole of some kind. Right? And the black hole versus neutron star, that depends on the total amount of mass that thing has, okay, in the middle. And so how it happens is something we'll kind of get into tonight. So I hope you guys can strap in. I also wanted to mention that we have purchased all the equipment for Sky Tour Benson. And so we have most of the equipment. We just need the camera. But we're getting the additional equipment we need. It's been ordered and paid for, thanks to amazing donations from Sky Tour patrons on our Patreon. And we are changing the mount of the telescope in Sky Tour Sonoran, and Sky Tour Benson. They will have the same mounts each. So that means that the telescope will be sitting like that telescope you see right there. Okay. It's on a fork mount. Okay. It has forks on either side, but you can see there's one side, there's the other. Okay. Those forks, all right, they're problematic, especially when you've got something sticking off the front like we do. We got this thing sticking off the front that's a dew shield. And if that goes down too far, it could hit the bottom of the telescope right here. And that's happened. And that's no good. That's what we call NG no good.
No bueno.
No, it's muy malo. That's la verdad. So what we want to do is get rid of those forks. And we're going to replace it with a mount that doesn't have forks. It's called a German equatorial. And we're replacing it with a Skywatcher series of mounts. If you look up Skywatcher telescope mounts, you'll see what we're talking about. Yeah. And these mounts are better for the telescope. They can handle the weight, of course, and they work the same exact way. So we don't have any dangers with a camera on the end or off the nose of the telescope. Our camera's sticking out the front of the telescope here. So we have a camera here, all right, and a lens system right there on our telescope in the Sonoran. Right. And that telescope has this lens sticking out, and then it has the camera sticking off that, and it has this dew shield around all of it. Okay. That's a lot of equipment. And a lot of expense sitting on the end of the telescope that can get sheared off if we
It's
go the
about
wrong way.
that wide. It's
Yeah,
yeah.
you
It's
know, you've you've
yeah.
you've you've taken it off
Mhm.
many times.
Mhm.
You know, I remember you going out there to clean the thing because we ended up having some lines appear on our
Yeah.
camera.
That was fun.
Yeah, yeah, fun. Listen to her.
It was fun. I get to learn so much by dealing with the telescope, and we all have so much to learn. So it's
Yeah, it's
very
true.
cool.
And I
Mhm.
thought you did a marvelous job out there. So one of the things that we want to make sure we do is we want to make a system that is robust because the
Yep.
time is going to come when it won't be just me operating these telescopes.
You
Tara,
say? No.
Tara. There'll be other people that can operate the telescope too, and maybe,
Wonderful.
yeah, maybe.
Mhm.
But you see, it's going to always be within the context of a stream. So, in other words, whoever is running the telescope is going to be running it for everybody, and the world is going to see what we do. Okay, this is a public
Yeah.
telescope. Okay, we bring you the universe live in real time. It's what we do, and when we actually get Benson up and running, we're then going to put in a third system. I've already got the equipment for that too. Okay, and that's a solar telescope. Now, what's
Ooh.
neat? Yeah, what's neat about that is you're going to see the sun. Okay, this is how the sun looks with that kind of telescope.
Oh, neat. Oh, I
Yeah,
was thinking the telescope ran on solar energy, but that's what our current telescope is doing.
that
So
is correct. Yeah, that's right. And so here, what you see on this screen
that's
here, this
neat.
is an example of the sun as seen in a specific type of light. It's light that's in the visible spectrum that you can see with your eyes, but you can't see it because the rest of the sun is so bright. It's
Wow.
called the light of it's hydrogen alpha light. So it's a emission of hydrogen gas on the sun that's caused by the very, very hot central energy within the sun going through the relatively cooler gas that's only 10,000 degrees
Oh,
on the
no.
outside, as opposed to 18 million degrees in the
I
core.
guess that is cool.
Yeah, yeah, relatively speaking, the outside
Yeah.
is very freezing. Um, and so that gas in the outside will um, actually absorb some of the energy that's coming out and it can re-emit it. And what will happen is the hydrogen atoms, in many cases, will start to emit at a specific frequency. And that specific frequency is what this particular telescope is tuned
Mm.
to. And this is what you see from it right here. So
Wow.
those snaky lines,
Mhm.
okay,
Hairs? Is
the
it
thing
sun
looks
hair?
it looks like sun here, right?
Mhm.
Well, if you look on the edge of the sun, you see those explosive things coming off the edge of the sun like that.
Right.
Okay, those are called prominences, and those things coming off the edge are also what the snaky things are that you see,
Oh.
but they're just coming at you.
Mhm.
And they're even cooler than the surface of the sun where these are coming from. And that makes them look even darker. And so that's why those look like that. So
Wow.
the telescope we have, this photo was taken with the very telescope that we have. So we're going to be able to show you details on the sun like never before. So we have a solar telescope coming, and we're going to have two deep sky systems. The one deep sky system everyone's used to is Sky Tour Sonoran, which is the one in the Sonoran Desert west of Phoenix by many, many miles. And it's out in the darkness of nothingness. Well, all you have to do is try and go there and you'll see, right? I mean, you're driving
Mhm.
miles and miles of dirt roads after you leave the regular tarred road.
Mhm.
So, um, and so that one is the wide angles telescope. It shows the wide view. It has a 1.5 by 1 degree field, so you actually see, it's like, you have 3 full moons across and 2 full moons tall
Wow.
on that one. But the one at Benson is actually going to be less than a full moon in size. It's actually going to be a much
Oh.
smaller field, right? And we're going to be also doing special photography with that one that you'll all be part of, and that's called narrow band imaging. And there's
Okay.
like going to be a filter wheel, which I have here, which we'll be bringing out there. It's got little places for different filters in the ring of filters, and the telescope will rotate the filters as needed to get to the different filters. We have one for
Mhm.
hydrogen alpha, that special hydrogen band that you just saw with the sun. We're going to have one for oxygen 3, which is the light of supernovae, which is this color, the green you see here.
Ooh, pretty.
That's right. Yeah.
Mhm.
These are all pictures we've taken.
Yep.
Okay. And you can see the red from hydrogen there and the green from
So
oxygen.
pretty.
Okay. And then we're going to have one for sulfur 2. The sulfur 2 is the ionized sulfur. And that's another one. And together, those three colors are what the Hubble telescope makes its images out of. So we can make images in the Hubble palette if we wanted
Okay.
to. I prefer realistic palettes, so I see things realistically. But, you know, if you're doing research, sometimes the Hubble palette helps you differentiate between one type of chemistry going on in a nebula and another. And that's what this
Right.
is all about. Okay. And then the camera that we're going to use is going to be a very good camera tuned to that particular telescope, which, by the way, is going to be an 11-inch Celestron telescope. The one we have in the Sonoran Desert is a 10-inch Meade telescope.
Right.
And that's the wide angle scope. And by the way, in case you forgot, that telescope in the desert that we have right now that you always look through with us, it runs 25 times faster than other telescopes of its kind because of this special modification called a hyperstar,
Right.
made by Starizona in Tucson, where Tara has been many times. I've been a few times. And the hyperstarred Meade telescope that we have is the only one on planet Earth. It's a prototype. It's never been done to these Meade telescopes. So I would say it's a brilliant success.
It is. It's awesome. So
yeah. So we want to make it last. We're going to change the mount to make it last because the mount goes haywire on our scope sometimes, and that's not acceptable.
Hey, Mark, I have a question if we can back up real quick on the solar telescope.
Yeah.
So you plan to stream those? So you're going to be doing streams during the day then? Is that what the plan is?
Yeah, the plan is I get no sleep.
I'm thinking, okay.
Yeah.
Wow, that would be interesting to do it during the day.
It will be. And one of the things, if something's interesting going on, like we just had the eclipse.
Yes.
I was actually looking at the eclipse with this particular telescope that I just showed you. And you see the beautiful hydrogen alpha details on the surface of the sun. And then you see the bite being taken out of it by the moon coming across. And you can actually see the bumps on the edge of the moon where the mountains are in the moon. It's really cool. And it's those bumps when it goes to totality. It's those bumps where you have some upper parts, some rises and falls in the mountains along the edge that give rise to a phenomenon called Bailey's beads, where you see bright blops of sunlight coming through the circular edge of the sun, circular edge of that eclipse briefly. And Bailey's beads is the result of light coming through the valleys and the lunar mountains that are at the edge of the moon.
Is that when it sometimes looks like a diamond ring or something? The
diamond ring is another feature. Yes. Okay. It's another feature of an eclipse. Exactly right. And that's really pretty as well. Yeah. I've seen totality once. I went to Vermont and we couldn't get anywhere near where we wanted to get. So we ended up settling for a bridge over a very deep gorge. So yeah, we were like about 500 feet or more above the raging torrent below. Stopped in the middle of the road, took out our telescope, set it up right there in the road. All right. And
don't do this at home, folks.
They can't. They got to go to Vermont for this gorge. Yeah. So it was pretty cool. And it was neat to see it when totality came through, because as it came through, the temperature dropped 25 degrees. Yeah. And it will. And you could still see before the sun was fully covered. You could still see it was too bright to look at. You couldn't look at the sun. It was too bright. However, the light everywhere around you looked dimmer and took on a less saturated tone. It looked more red, even though it really wasn't. And so what happened was you got the feeling that for the first time you were at a world where the star was one of those M-class stars, one of these small red dwarf stars.
Oh, that's how it would be?
It felt like that, yeah.
Interesting.
Yeah, for that brief amount of time, which lasted about maybe 2-3 minutes at the time. And then when the sun came back, it's like it's immediately brighter, because you're leaving the shadow rather rapidly. At the International Space Station, they actually imaged the shadow of the moon crossing the Earth, and it looks like sci-fi. It looks like this black soft-edged disc moving across the Earth,
Cool.
like the Earth was collapsing from a black hole or something. Yeah.
That's
But
awesome.
yeah, and don't forget though, and that is the thing that when this eclipse occurred, it was one of the longest, like 4.5 minutes. Now, people were saying, "Oh no, NASA's going to launch rockets into the eclipse," which is that makes no
Why?
sense. It makes no sense. Those words
Why?
don't make sense. And then they were going to they said, and then CERN is starting up on Monday. There's something going on. Yeah, that's right. It was the beginning of the work week. That's why CERN was starting up. Okay, to be fair, okay,
Oh, closed
they're
on Sunday.
investigating. Yeah, right. Let's be fair. Scientists don't work every single day, and so there's a lot of that false narratives going on out there. And as you can see, I mean, I had people saying it's the end of all things. It's like, okay, yeah, I can see where the end of your education was. Okay. And I know that, for instance, at CERN overseas, they never saw an eclipse. The eclipse was only from the Eastern Pacific into Mexico, up through Texas, up through the northeastern United States, and out into the middle of the Atlantic. And that was it. The moon moved far enough after that the rest of the Earth never even got to see the eclipse. It was only a few miles wide of totality. So even in the United States, most people didn't even know there was an eclipse going on.
I got to see this last one with my glasses. That was pretty cool, but it
Yeah, was it
wasn't
though?
full. It was. It's just really fun, and I did get that sense of the sky dimming somewhat.
Yeah.
You did sense that.
Yeah, I
Pretty
think
cool.
you had. I forget what the percentage
It was
was.
like 70 or 80 something, or no, it wasn't that.
No, not that
I don't
one. I had
remember.
92 here.
Yeah. It was
Yeah,
definitely less.
but I remember, I think up in Seattle it was 13% or something like that.
Wow.
So no one would even notice that. And until the last 1% of the sun is gone, you can't look at the sun, literally, because when that 1% is still there, it's too bright to look at, and your brain is saying, "Look away, look away." Okay, but when it goes away and you see totality, you can look at it with your eyes because your brain tells you when to stop looking at the sun. Okay,
It
but
hurts.
that's right, and you don't do it with binoculars ever. Okay, because that's a
Oh, okay.
recipe
Good to know. Okay.
recipe for destroying your eyesight. Yeah.
Mhm.
Yeah. And so, you treat the sun during an eclipse the same way you do when it's not an eclipse. You never point a telescope at it. You don't point binoculars at it. You just, look at it with your eye. And then when it comes back, you say, "Oh, okay, we're back," and that's what you do. Or with your glasses, of course,
Mhm.
or an approved solar telescope like we have.
Yeah. Or you can take a cereal box and poke a hole through it, and there's
Thank
little
you.
things you can make to
I
look
made
at it.
I made a pinhole viewer for others
Yeah.
to see it on the day of the eclipse. Yeah.
Yeah, that's how I always used to do it.
Yeah. I poked a hole. I just poked a hole on a piece of paper, and it was a big piece of cardboard. And then I had another piece of cardboard, a white cardboard on the ground, and just held it over it. It's like, look, there's the eclipse.
It's amazing. It's a little camera.
Yeah. And if you don't have that, all you have to do is walk up to any tree and look at the shadows being cast by the tree, because the confusion between the branches will cause thousands of pinhole cameras.
Oh, I should have done that. Darn it.
It's an extremely artistic thing too to see.
Yes.
Yeah, because the shadow is not just like continuous. You've got all these little crescents. You'd see all these little crescents all over the ground. It's like, whoa.
Awesome. Okay, next time.
Yeah.
Next time.
Yeah, I mean, you only got a few years.
They happen so often.
Well, solar eclipses are way, fairly often, but the one we had was rare only because most of the United States saw it.
Okay.
Yeah, that's the only reason it was rare. It didn't have any special meaning, and all the I think it's funny, right? Because all the special meaning that people say this eclipse was going to have, when it didn't have it, where'd they go? Well, they went back and hiding. It's like, no, did I hide me? I didn't say it. No, I didn't say anything. Run away. So yeah, all the people that make these wild, crazy statements, they vanish into the woodwork when it doesn't come true. And it should be held accountable. I'm willing to hold them accountable. I'm willing to hold them accountable. Yeah. So now our sun, course, is a regular star. It means that it's a kind of an average star. It's nothing special. It doesn't have a very high temperature. It's 10,000 degrees on the surface. It's 18 million in the
Wow.
core. Okay. The core is
Awesome.
small, and that's the only place that nucleosynthesis, where the hydrogen is being turned into helium, is occurring. All the rest of that huge envelope, it's a million miles across, almost
Wow.
860,000 miles across. That's all protons and electrons running around by themselves in the plasma. And that's just the stuff the star was made of. And the weight of those materials pressing down from their mutual gravity, all concentrating at the core, is what
Yeah.
gives the core its temperature and the
Mhm.
ability to do this fusion thing. And it's really cool that this fusion thing can occur, because without it, well, we wouldn't be here, you know.
Do we know how big the core
mm,
is?
yeah, no, the core is. I can get you the exact size of the core probably after the break. I don't want to. I mean, it's a number that
But is it like miles, or is it tinier than that?
oh no, it's gonna be many miles. It's probably gonna
Yeah.
be. I'm gonna as a guess. I'm gonna say it's probably a little larger than the Earth, maybe a little bit
Oh,
more than
okay.
that. Maybe the size of Jupiter, possibly. I have to look.
Wow.
I don't
Okay.
know.
Cool.
Between the Earth and Jupiter, I'm gonna guess. Okay, if I'm wrong, well, I'm wrong. For my when I was getting my degree in astronomy, Tara, and I think I told you this once or twice, maybe too many times. One of the things I had to do was create a computer model of a star, and we had to have a core that was undergoing fusion, normal fusion, and then the outer envelope of the star. We had to model this and make sure that every step of the way we could consult every step of the way, miles out from the center of the star, and get proper results for what should be happening out there. And you got to keep in mind that
Interesting.
you can have for a certain distance out, it's all called radiative. It's a radiation, all this spewing of very, very, very high energy radiation in all directions, right?
Okay.
Then you get to a certain point, and then there's a mixture of radiation and convection, like a pot boiling on the stove. Okay.
Roiling, sort of.
That's roiling, exactly right. And
Mhm.
so we had to model that transitional zone as well. It was
Oh.
very surprising to see how much of the radiative and convection zones were mixed into each other. And then the outer parts of the star are all convection, which is why when we look at the
Interesting.
sun image like this, you see
Mhm.
on the surface of the sun there, you see all these little uh, areas that look like dark little spots,
Looks like an
little
orange.
yes, the orange peel skin.
Mhm.
Thank you. That's a very good analogy.
Yeah.
That orange peel skin is actually a location of objects that are called granules. And what these are the convection zones. And the stuff comes up that's hot, boils over the edge and goes down the sides. And around the sides, because it's now cooler, you see a dark border.
Oh.
So one granule is one boiling pot. So you get this one thing coming up,
Literally.
and then it goes down. Okay.
Mhm.
And so
Interesting.
the sun's surface at this level into it, called the chromosphere, where this is actually a convective surface. So it's actually boiling, and you can see those granules changing. Now, suffice it to say, the granules in some cases are bigger than the entire Earth. One granule. Okay.
It's hard to comprehend, but yeah.
Yeah, and most prominence is
Mhm.
those flares that are coming off the sun that we see. They're always all bigger than the Earth by a long shot. So it's really impressive
Mm.
how big these things can be.
Yeah.
Now when we talk about stars, and we talk about that's the kind of thing that happens with other stars. Now the small M-type stars, they're cooler in temperature, right? They're redder. Okay. And guess what? Those stars actually have convection starting just outside their core and going all the way to the surface, and that
Oh.
means that there's a lot of material that can get circulated. So hydrogen out in the outer reaches here that may not get into the core to go into fusion in our sun, in the M star, it can be circulated down toward the core and be used for fusion. This is why those
Mm.
cool M stars last trillions of years.
Wow.
In fact, The M stars that existed when the universe began are still here. Okay.
Wow.
They're all still here. There's no M stars that have died yet because normal M stars, they're fusing hydrogen into helium. They're tiny little percolators. Some are just a little bit bigger than Jupiter. There's actually one we found that's actually smaller than Jupiter, but it's denser. So it can be a little M-class star at that level. It's amazing what we found.
Are they still making them? I mean, is the universe still making new ones?
Absolutely. Absolutely. In fact, every stellar nursery is pumping out stars of many different kinds. And these stars of many different kinds are actually very different types in some cases. So M-class stars are being churned out quite a lot. In fact, we know that because most of the most of the stars in the universe are M stars. The overwhelmingly vast majority are these small, cooler stars. And it stands to reason that most of these stars, these M stars, are also the stars that have the most planets around them. Okay. And that's kind of cool. Now, these are also stars that are locked to their star. They have, like the moon is locked to the Earth. One face faces the Earth, the moon. Well, the same face of the planet faces the star. That's called tidal lock. Right. And it has to do with the way gravity interacts with the body. It's so close to it. And so that tidal locking is something that, well, I look at it as an opportunity. And I've said this before, if you like sun, go to the sunny side of the planet, man, and hang out there. And you got to, you sit back and get a tan, sometimes an exceptionally really deep tan, maybe fatal tan if you're not careful. And then if you like sunsets, you go to the edge of the planet where the sun is always setting. And now you've got perpetual sunsets all day because there is no day or night. So the whole time. So there's no day or night on these things. Day is however long you're there. And night is however long you're on the other side. And if you like stars, you go to the other side. Okay. And just hang out in the dark.
I think I'd live along the edge. So, depending which way you're facing, you
could drive to the sun and you can drive to the stars.
Right. That'd be neat. Cool.
Wouldn't it be? Yeah.
Yeah.
And the planets are going to be about the size of the Earth, perhaps. So you got plenty of opportunity there. Now, the thing to keep in mind is, as wonderful as that sounds, if these planets have an atmosphere, keep in mind that on the sun-facing side, that atmosphere is getting pretty hot. Because it's never cooling off, right? So the star is going to continually heat that. So on the dark side, if you have an atmosphere over there, well, they're connected. It's one atmosphere. So what's happening on the transition from the light to the dark? There's probably going to be very, very strong winds blowing across that equator or across that terminator. Okay,
right.
And so from the warm side to the dark side, these clouds are going to probably blow around to the backside to mix the temperatures together. So overall, if it's, let's say, 95 degrees Fahrenheit on the sunny side.
Sounds perfect.
It's right. It's going to be probably 80 degrees on the center of the dark side, maybe a little less. Okay. Depending on the size of the planet, depending on how strong the winds are. But the winds might be pretty powerful, but you may very well have clear skies. Now, the thing about these planets around these very small stars is that when they go around the star, they are so close to the star because M-class stars are usually much less powerful than our sun in terms of their radiation intensity. So when the planet is far away from the star, like as far as Mercury is from the star, our star, like was it 38 million miles? Okay. That's like the Kuiper belt, in this little mini star system. Okay. Yeah. You have to have, in fact, all the planets in the solar system, we have Mercury that far from the sun. If you went to some of these M-class stars and you looked at their planets that were in the habitable zone, where they're not too hot, not too cold,
just right.
Yes. The Goldilocks zone. Yeah. Well, you would find yourself being well within the orbit of Mercury to that star. And that's the habitable location, right? But that means you're orbiting the star faster. Mercury takes 88 days to go around the sun at its distance. Some of these planets go around, some of these planets go around these M-class stars in like 6 days, 13 days.
Wow. Mark, I have a question.
Mhm.
The habitable zone, habitable, that zone that we can live at on these
Yeah,
planets. So
habitable. Yeah.
if we're going to look for planets that we can maybe go to in the future, do we have a better chance at zones that are closer to the planet, or can we go to any of them? Do we have to? I mean, what chance does a human have in the habitable zone? Why can't I say that word? Zone in a like an M-class star, because it's so much closer. Would that be an issue with how our biological systems would be, or anything?
Well,
Or
um, yes, because we would have to evolve if we lived in the sunny side of an M-class planet, star, okay, star-class planet, okay. If we were in the sunny side, we'd probably have to evolve a skin that could resist ultraviolet radiation a little better than the one we have now, because these
wouldn't
stars are
burn.
known to be flare stars. They give off some pretty strong ultraviolet and flare and X-ray flares. So we'd have to be a little careful with that. But that said, the far side, the dark side, might be more habitable for that reason, because it would never see the direct results of an impact from one of these flares, except the really cool auroras. Oh, they got the auroras. Well, I guess the front
That'd
side's
be neat.
getting baked. Look at that. Look at those auroras. But still, I mean, we're talking about planets that are, tidally locked, and so most likely you're going to find that most of the habitable planets in the universe are going to be around these M-type stars. So we ought to be thinking in terms of how life could evolve around M-type stars. And so that way we'll be ready when we start looking. I mean, the James Webb Space Telescope is able to indirectly see oxygen in an atmosphere of a star's planet. And so I think that's something that's like the first thing we check off: oxygen in the planet's atmosphere. Okay, that's good. Okay, so that means that carbon-based life forms could possibly exist there if the atmosphere is thick enough, if the planet is stable enough, if the star is stable enough. And each of those things is important to consider, and it does remove candidates, but you're left with, the potential for up to 400 billion stars in our galaxy alone.
Wow.
And so, I mean, that's at the high end. The low end, it's 100 billion. Go figure. What's a billion? What's
give or
100
take.
billion? What's 100 billion here or there? Count to 100 billion. It'll take you the rest of your life. Yep.
Not if you do it by billions, like 100 billions at once.
That's true. That's right.
Interesting. Okay.
All right.
Sorry.
No, it's fine. I love your question. So, yeah, and I'll just take a sip of water here. It's better.
But not as when we're saying that there's these billions of planets habitable planets out there. That doesn't necessarily mean they're habitable for us, right?
But it means that there's liquid water on the surface, and if it has an atmosphere that is conducive to life like us, then we would consider it a habitable planet for us. But you're absolutely right. Think about one of the Kepler planets that was discovered. It's actually what's called a Hycean world, Hycean. That means hydrogen atmosphere. Yeah, we don't breathe hydrogen, do we?
Not now.
No. But the interesting thing about that is that the Webb Space Telescope was looking at this planet and deduced so far that it looks like, and this is all going to be confirmed, it looks like this is a planet that's going to be a water world, just like in the movie with Kevin Costner, a water world where there's no land potentially. And they also discovered a signature of a very interesting compound in the atmosphere of this planet's hydrogen gases, and that was dimethyl sulfide. Now, dimethyl sulfide doesn't mean much to anyone listening to this unless they know the ocean, and that is, here on Earth, dimethyl sulfide is only made by life. It is
Hmm.
it's known colloquially as the smell of the sea. When the tide goes out, that stink you smell, that's the organic refuse poop
Is that
of
like the
sea.
tidal mats things, sort of?
I don't
Someone
know.
has the word for
There might be a component of dimethyl sulfide in one of those
them.
mats, but I can tell you that dimethyl sulfide, if that confirmation comes through, the James Webb may have discovered life on another world.
Wow.
Think about that. Isn't that cool?
And that would be the first time,
That's
right?
absolutely even more,
More than cool.
and long before we even found out whether it's on Mars.
Isn't
You
that
know?
interesting?
Yeah,
Hmm.
yeah. So
So
go
hopefully they'll
ahead.
find out soon. I wonder what the timing would be on something like that.
I'm not sure. I'm not
Mhm.
sure, but I do know that I do know that the planets around these stars are conducive to habitable zone life. And
Nice.
to your question about whether life would be like us or not, around the hydrogen world wouldn't be like us. But again, it could be carbon-based life that uses different metabolism, uses different metabolic processes to make
Mhm.
energy to survive. And I'm open to all that. I just don't know if it's really. I don't know where this could possibly lead. You know, but
Well,
can you
yes.
imagine?
Oh, if there's intelligence behind this other type of carbon-based life, or
Yeah,
something, that'd
yeah.
be
Who
so
knows?
amazing. Yeah.
I mean, intelligence is not a final destination. It's one
Right.
potential path. And but with
Interesting.
all the potential habitable planets, it kind of makes the odds a little better that you'll find it somewhere else,
Right.
you know? So, but
Mhm.
that's on stars like our sun, stars like these M-class stars. That makes sense. If you go to the stars that are much more massive than ours, well, then that's a very different thing because what ends up happening is these stars they go through their hydrogen in the core very quickly, and the hydrogen's converted into helium. And once the helium's converted, all converted, and there's no more hydrogen, then the process starts to slow down, and the star begins to
Mhm.
contract. When it contracts, that pressure gets hotter and hotter in the core, and boom! All of a sudden, the helium can start to burn. And once
Mm.
you get to 100 million Celsius, then you can start making helium into things.
Wow.
And that's you're thinking periodic table here, right? Because that's where the periodic table comes from, is from stellar processes in
Mm.
part. So
Wow.
when the core of that star that's run out of hydrogen and is collapsing, when that core reaches 100 million Celsius, now the helium that's in that core can now fuse and become carbon and isotopes of nitrogen and oxygen next. And so that star, once that starts again, the star begins to bloat and it gets really, really big. And it forms, in fact, just before the helium starts to burn, that compression of the core causes the outer regions of the star to really expand rapidly. And that's when the star becomes what's called a red giant.
Oh,
And
cool.
it has extremely high core temperatures because there's so much mass in there, right? And so then when the helium starts to occur or starts to fuse, then the star kind of reaches this equilibrium for a while. And so it may shrink a little bit, lose a little of its brightness, and now it stabilizes. And now it's making helium into that nitrogen and carbon. But once that runs out, what happens? Well, then it begins to shrink again because gravity is always trying to collapse the star, and the radiation pressure pushing out is holding it up. So it's
Right.
an even battle of pushing outward versus pushing inward. So that's called hydrostatic equilibrium, where they maintain that equilibrium. But once one starts to fade a little bit, then this one can push down, and then once this one gets a little stronger, it can push out. So that happens several times in the life of a star. And
Cool.
once the star fuses elements uh, beyond element 23 and 24, once it gets to element 25, which is iron, okay, that's a problem because iron can't be fused into anything beyond that
Hmm.
because it usually, and see what happens is fusion gives back energy. Okay. When you fuse hydrogen into helium, okay, yes, you make helium, but you're getting energy out. That's much more than the energy you put in. With iron, on the other hand, you have to put in more energy than you get out. So it's naturally can't go beyond iron. So iron is the last step in the evolution of element creation in a star.
That's neat.
It is, and it's scary as heck, because the next thing that happens is the most incredible set of processes. So, these massive stars that have these iron cores, they're very, very hot in the center compared to these lower mass stars, and that higher temperature results from the higher gravitational pressures squeezing the star together. And that's something that is very natural in the universe. It's something that happens all the time. We see it a lot. Okay, but what happens now is these stars make these heavier elements in their cores, all the way to iron, as I said, and it's these massive stars that can make more elements in its core that actually create what's called a neutron-rich environment. They can actually, in these massive star cores, the temperatures and densities will allow for many different types of isotopes. That is, nuclei, because there's no atoms in there. It's all nuclei. It's protons, okay, and free electrons, okay. It can allow for protons to share space with and allow in many different types of many neutrons to make many different types of variations of the same atom. So you can have iron 56. You can have iron, normal iron. You can have nitrogen 15, nitrogen 14, carbon 12, carbon 14. Okay. And what does that mean? It means that you have a certain number of neutrons in the nuclei of all these atoms that make it a different type of the same atom. Now what happens in this case is when you are in the later stage of stellar evolution, where the last item, the last element that could possibly be fused is done. That's silicon. Okay. Silicon fusion in a big star lasts for literally 1 day.
Oh my goodness.
1 day out of billions of years. No, those stars, millions of years. Okay. They live a few tens of millions of years, sometimes less. But for 1 day, they'll fuse silicon. And when that happens, when that stops happening, it all stops suddenly. And so now, remember I talked about this pressure pushing, this is gravity pushing, trying to collapse a star. That does happen. But as it happens, okay, there's a number of things that go on. And we've talked about supernovae in the past. And this particular process is called core collapse, where now there's nothing to push out radiation. So gravity's going to win, and it's starting to crush. And it begins to do that. But what happens is when it does that crushing process, all right, we also have this effect where all this material is coming in and hitting the core from all sides. And the core is this inert iron. It can't go any further. So what happens? It does this. The stuff coming into the core goes boom, and it goes boom, and it bounces off. Okay. Think of it as a rebound. And that rebound now forms a massive cataclysmic shockwave heading out from the star. Now the rest of the star is collapsing in, and now much of the star is now going out at the same time. That's a recipe for disaster. And what that does is it rips the star apart in what we call it a core collapse supernova, don't we? Right? Now, in that process, okay, while the core is collapsing, a lot of things happen under these extreme conditions of temperature and pressure. They lead to a process called neutronization, like Jimmy Neutron, right?
Neutronization. Okay. That's a big word.
That's your word for today.
Neutronization.
Okay. Yeah. And what happens here is, remember those protons and electrons I told you about that are floating around in there?
Yep. They're free.
That's right. Well, now the protons and electrons under this type of extreme pressure and temperature, electrons actually combine with the protons to form neutrons. It's called neutronization. And this is something, it's during the collapse phase of the core collapse supernova. It's the last step in the star's life. All right. And so you end up getting all these many neutrons in there, and that's all going to happen within the stellar core. So when the supernova occurs and blasts off all the outer layers of the star, remember the core is just the one little tiny part that's fusing. All the
Mhm.
rest is what the star was made with. All that gets blown off, and what's left is that core. And if that core has had was a massive core based on the fact that it was a massive star to begin with, making all kinds of elements in its core, well, then that massive star core is going to be composed of primarily neutrons. And that's where neutron stars come from.
Yeah.
That's how they form.
Wow.
Yeah. And the thing is, some of those neutron stars can have hot spots on them. Okay. Those hot spots. Okay. Now, there's also, when you have a core collapse like that, it might cause that core to rapidly rotate very, very rapidly. And that rapid rotation can be something we can see because these lighthouse beacons of hotspots on this neutron star might flash by us, like as it goes by. So we'd see it every time it comes by us, like the lighthouse swinging at us. This is something that lighthouse beacon effect is something we see with the Crab Nebula. The Crab Nebula,
Oh, yes.
remember that? Spotted in
Mhm.
1054 AD by Chinese astronomers. They saw it with their eye. We saw it with our telescopes. We noticed this amazing remnant, but then at the center, we noticed something. We noticed that in the center, there was this neutron star there, and it was actually pulsing at us 33 times per second.
Wow, something that big moving that fast.
That's right.
Crazy.
Now,
Mm.
let's talk about what does that
Oh,
mean?
wow.
Something that big. What is big? Well,
Fun.
a neutron
Yes.
star. Okay, remember our sun was about 860,000 miles across. The stars that collapse can sometimes be so big that their diameters are the diameter of the Earth's orbit or Mars orbit, sometimes even Jupiter's
Wow.
orbit. Okay, diameter. Okay, out on either side. So when those stars collapse into a neutron star, the size of the remaining neutron star is pretty crazy. This is an example.
Oh, that's cool.
That's Chicago, and that's a hypothetical neutron star sitting over Chicago.
A small
It's
one?
it's literally, well, they're all about the same size.
Okay.
This neutron star, these neutron stars are literally only a few kilometers across. After
Mm.
all that mass they have on them, what's left is only a few kilometers across. But it's a lot of mass that's compressed and compacted in there. And so that compaction, if you took a teaspoon of that stuff, okay, there's two things that would happen. Let's say you could do it. You could take a teaspoon of that material, bring it to Earth, and weigh it. Okay, what would it weigh?
Probably more than the Earth.
It'd weigh billions of tons. Probably not more than the Earth, but still
Okay.
a teaspoonful.
That's a lot.
Would weigh several billion tons, actually. And so that's the first thing that would happen. The second thing that would happen is as soon as you pulled it away from the star, well, then there was no more force acting on it to hold it in place. It would just go, it would just go,
Right.
probably explode in all directions at high speed. But we can ignore that. So when we look at a neutron star, then it's mostly neutrons. And here you can see an image of what a neutron star actually looks like. This,
Oh, nice.
yeah, this you can see there's an inner core, there's an outer core, there's an inner crust, an outer crust, and there's actually an atmosphere. Now, the atmosphere is a rarefied gas that is just on the surface of the neutron star, a remnant. And this one is meant to be like a pulsar, which is one of those neutron stars that flashes and winks at us. And that's one of those hot spots that we're seeing there, right? And then in the inset, you can see that there is a magnetic field around that star. Well, in some cases, these neutron stars have such a powerful magnetic field that if you got anywhere near them, your body would be ripped to pieces.
Mm.
Okay. These are called magnetars. And these particular stars are so powerful. They are the universe's destroyers because
Wow.
they will rip apart anything that comes anywhere near them.
Wow.
Yeah. And now, if you want to see an actual pulsar, we took this image. This is an image called the Jellyfish Nebula.
Oh, nice.
That red star to the right there, that's called Propus, and that's not part of this nebula. Okay. But this is a supernova remnant. And you can kind of see, and if I can just take it away from it, you can kind of see how it kind of went like this. Well, it went like this. It went out in two directions, right? It was like that. Boom, went out like that. Okay. So when you look at it, you can see that right there. Right.
Oh, yeah. Mm-hmm.
Yeah. Now, the neutron star that's remaining from here that we photographed, I'll show you here in a second. It's actually near the bottom of the image. It's not where, if you draw like lines back from the arcs and so forth to try and find the center, you're not going to find anything there. There's nothing there. Okay. The neutron star that actually caused it, because of that differential pressure during the supernova explosion that occurs, the neutron star got motion imparted to it.
Wow.
And it got kicked out of its own location. So, yeah, inside that nebula, that arrow points to that blue thing right there.
And that's it.
That's the neutron star.
It's amazing that it can be figured out and you can find it amongst all those other stars. And we have less than a minute, by the way.
I know we do. You're right. Thank you. And you know what's interesting about the neutron star?
What's that?
This neutron star is thousands of light years away, and it's only about the size of Manhattan Island.
Oh my gosh.
And we're seeing it because it's so absolutely bright.
Wow.
Isn't that incredible?
That's neat.
So if you look at this image again, it's down near the bottom of the image, not quite near the bottom, but go to the center and go down. You'll see a little bright area, and it's just below that bright area. If I bring it in again, you'll see it.
That's neat.
Yeah, there's the neutron star, the blue thing right there. Yeah. Yeah, and it's distinctly blue, and that's what tells you that's the neutron star.
That's how you found it.
Yeah, and you know why blue? Because blue is the hottest temperature in the universe is blue.
Right.
And neutron stars are excruciatingly hot. And
Cool.
they do well, speaking of cool, they do cool off over time. And they also spin down. The Crab Nebula pulsar, a neutron star, goes 33 times per second. And the fastest one, ready for this?
Yep.
Over 700 times per
Oh
second.
my goodness.
Yeah.
That they can even measure that is crazy.
Yeah, I know. And it's yeah. So this is what we're talking about. And when we come back, I think we're going to dive into some black holes too. And
cool.
Yeah. And
not literally.
Oh yeah, that would be the end of us if we did, huh?
Yeah.
And if you have any questions out there in the chat, let me know, because I will certainly be digging through anything in the chat tonight and ask you or bring on your question. So we'll be back right after these words. Thank you, guys.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
As UFO reports come in from around the world, the Mutual UFO Network, MUFON, is there. We continue to explore new cases and build our massive database. We share our information with the world in a number of ways. If you would like to be part of our investigative team, you are always welcome. What could be more exciting than exploring the UFO question firsthand? Join MUFON, find your friends.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Hey, welcome back. It is I, Mark D'Antonio, I think.
It looks like you.
Okay, thank you. Hey, look, I can have my doubts. So, how has your week been, by the way, Tara?
Been excellent, thank you. Great weather here, so
Yeah,
I hope everybody's having a good week.
It's about 73 or so here today, so it was very nice. Yeah. I spent the day filling in the driveway where the water gouged out a foot deep ruts all the way down the 150-foot length.
Oh my gosh, that's a long driveway.
Yeah, and that's just from the top edge. Then it goes all the way down. You know, it goes 150 feet to the road, and at the top is a 50 by 50 turnaround. And I gotta say, that's a lot of work.
It sounds like it.
Yeah, I'm sore a little bit, but it's all right.
Well,
Yeah,
I bet it looks good though.
Yeah, we need the exercise, don't we?
Mm-hmm. Everybody does, yes.
Yeah.
Stay active.
Yeah, that's great. That's right. Agreed.
Mm-hmm.
I was saying hello to some folks in the chat here earlier, and it was very nice to see folks out there. Yeah. I know I see Kathy and Jane is out there. Water Rat's with us. Water Rat is a guy that actually used to work here for me. His name's Matt. A great guy. Ronald is here. OG Skywatch. Christine Anderson asks about the green comet. It was low to the horizon, Christine, and so when it was low to the horizon, and I'll just bring it up. When it was low to the horizon, our building blocked being able to move the telescope low enough to see it.
Yeah,
I tried actually, and we can't do it right now. So unfortunately, we're stuck not being able to do it. But it's okay. Like as I said, we're adding the next observatory in Benson, Arizona. We broke ground. I was looking for pictures of it to show guys, but I apparently only put them on Facebook, and I didn't actually bring them over to my local machine. It went right from my phone to Facebook, and so I go find that post and bring them down, or connect my phone. Bottom line is, we actually ended up in Benson. We did the X marks the spot thing, took pictures of it, figured out how we're going to get power to it. We've got that planned out. And Terry, you got to get there to see it too, because I don't know how far Benson is from where you are. Probably a little further than where Marianne is.
Yeah.
Yeah, you're probably another 45 minutes away from it.
Mm-hmm.
Yeah.
At least, yeah.
Yeah. But the nice thing is, one of the people that works at Star Arizona lives right nearby. And he just happens to be the guy that I deal with most of the time. Star Arizona is your one-stop shop for everything astronomy in Tucson, Arizona. If you haven't talked to Steve or Dean or David at Star Arizona, I can't recommend them more highly. They are just phenomenal people. So this is kind of a commercial for them, although they're not officially sponsors of any kind, but they do supply us with this amazing equipment. But I do want to mention that Tara and Marianne have driven this telescope, Sky Tour Sonoran telescope, down there quite a lot. to have little repairs done to it, and it's all because of that fork mount that we're talking about. Okay, that fork right there, that fork, these forks got to go. These got to come out because all the mechanics is inside that, and it causes problems.
And it's hard to get repaired parts or replacement parts for some of that.
What
So,
she did, what she said, yeah, Mead parts are actually impossible to find. I actually had an opportunity to buy a 16-inch Mead. I don't know if I told you this. Yeah, I could have picked up a 16-inch Mead telescope for $5,000.
but you didn't.
Considering they're
Because,
18,000.
oh my gosh.
Yeah. And why would you think it's being sold so cheaply? Because they know that if it breaks down, you can't get parts.
Mhm.
So I said, nope, not even going to entertain it, because I'd much rather get a telescope that's supported, has parts available, than get something that is not going to be serviceable. And that's what we're doing. We're just making sure we have serviceable parts. And those of you that have seen us on Sky Tour, and Tara knows this, have seen some of our imagery, you know that we get stuff in 20 seconds that takes minutes to hours to capture. And we're doing it all in one shot. And that's what we do. And that's why we do it. We do it because you guys are just hungry for this stuff.
Well, it's inspiring and it's that instant gratification, but then you see how beautiful it is and you just want to see more.
Yeah. And so you say, oh, now these pictures were taken, but now it's gone because that jerk Mark, he deleted it. No, I didn't. I saved it to our server where all of you get to go and take down these images for free. Zippo. What do you pay? Nothing.
Nada.
Nothing. Nada. Nunca.
Just your time to go look them up and download them.
That's right. Yeah. No más dinero. I mean, you guys can get them, and all you have to do is look them up. Yeah, and exactly. Now, Isabella, who is in our chat tonight, Isabella is one of our viewers from Bulgaria. Isabella has done a lot of work recently on the heels of Robin Curtis, who did a lot of the database stuff for us before. And Isabella has taken up the charge, and she has literally completed all the data for 2021, 22, 23, and 24. So now we have 4 years of data that we can search on and go looking for differences. So over 4 years, would much change? Maybe not. But Isabella found asteroids, already.
Very cool.
Yep. And she found stars that may or may not be there. We've got to further look at that. In fact, there are people doing studies on stars that are vanishing in the sky, and the vanishing could be related to data collection techniques, artifacts, or it could be that something real is happening that we don't understand yet, and that's kind of cool. And Isabella took it upon herself to do that, and so we're really proud of her. Show her some love in the chat.
Yay! Thanks, Isabella.
Yeah, she did some really, really nice work, I have to say.
Yeah.
And it's not over yet. I mean, it's just incredible. There's so much that she's done, So that said, we were talking about these collapsing massive stars. If they go beyond a certain amount of mass, where that's left behind in the core, then you're going to find that the star may continue to collapse past the neutron star stage. And there's a few stages that a dying star can end up in. It can end up in a white dwarf stage, which is a stellar core remnant the size of the Earth. Okay. And that is a object which is held up because of something called electron degeneracy pressure. We talked about how there's free protons and electrons in the core that are running around. Well, if you pack them in really, really, really close, the electrons push back pretty hard. And you think of a checkerboard, and every checker box, every checker square has an electron in it. You can't have two in any one square. So once you fill up all the checkerboards inside the star with electrons, they resist being pressed further. Okay. And that's the process that happens. And if it's not a lot of pressure beyond that, then the star stays as a white dwarf. Okay. And this pressure that the electrons are pushing back with will hold the star up because it's trying to collapse from its mass. Okay, so now taking it a step further, continue that pressure and crushing, and then what happens is what we talked about before: the protons and the electrons combine to make neutrons, and you have a star made of neutrons, which is what we get with a neutron star. Wow. Excuse me. I just haven't talked this much for some time. So.
It has been a while.
Yeah. So yeah. Anyway, and people are showing their love for Isabella now in the chat if you haven't seen it. So excuse me. I'm telling you, I have to mute probably to cough more. All right.
You've got a cough, I got a barking dog, so
What dog was that?
That's Honey, and I'm the only zookeeper today. So
yeah, Honey is she's a pretty girl.
Yeah, she's a good dog.
I've met Honey a few times.
She's just elderly.
Yeah, I have one of those.
Yeah,
14-year-old.
Little dingo. Yeah.
Little dingo is 14 years old. Yeah. So let's consider now, if a neutron star is made, if a star has even more mass, and that's around 2.4 to 2.5 solar masses in the core, that's about the maximum size that a neutron star can be. Beyond that, it can collapse even more, because now the neutrons literally are getting crushed even more. And this leads to the concept of the black hole. Now, black holes are thought to form when massive stars undergo gravitational collapse at the end of their life cycles, like we talked about. If the star is massive enough, it can collapse under its own gravity into this object we call a singularity. Now, I'm going to define that, because classically a singularity is an object that is infinitely small, right? Well, you're not going to find any astrophysicist or cosmologist or astronomer that's going to say that they believe that there's an infinitely small spot in the middle of a black hole, because there's not. Okay, that has to do more with how we calculate gravity. We calculate gravity, say, between the Earth and the Moon, by calculating the gravity at the center of the Earth, the gravity at the center of the Moon. Okay. So that's like a single point in the middle, at the very, the center of mass of the object. Same thing with a black hole. The singularity concept doesn't mean a tiny, infinitely small point. It means that we would calculate the gravity as if it's acting at the center.
Oh, interesting.
Yeah. And so let's suppose that a star has collapsed down further beyond the neutron star size, till it gets to a point, all right, where if it's more massive, it gets to the point where when it shrinks and shrinks and shrinks and there's more mass in there, you can imagine that it's going to start bending space, because that's what gravity does. Gravity bends space, all right?
The fabric of space, right?
That's right. It bends the fabric of space. And, the concept of fabric of space is another concept which I know people just have to sort of take for granted. But space is not empty. There's a medium there in a sense, and it can be bent by gravity. And gravity is pretty much the only thing that will bend space. So we've seen, for instance, that we have a giant galaxy in the foreground and a smaller galaxy cluster in the background. And we can see that the galaxies in the background are distorted because of the gravity of this big one in the foreground.
Oh. Okay.
That's called a gravitational lens. And so that happens often when we look at galaxy clusters. We see that, right? So you can imagine that an object like a black hole would get massive enough, small enough, such that it gets to the point where it would bend space so deeply that when light tries to go past it, light will be curved. Here's what light does in general. Light follows the curve of space. It's like a car on a hill. Okay, if you have a car on a hill, the car has to follow the hill. There it goes. There's the car. Okay. Well, if it's space that's curved, light is like the car. It follows the curve of space. So when you have light following the curve of space, if space is curved deeply enough, the light will go in and start to follow the curve, and it'll just keep circling around and never get out. Light is not affected by gravity. Okay. Light doesn't have mass. Photons have no mass. So what does that mean? Why can it be stopped by gravity? Because light follows space, the curve of space. And if space is curved, light follows the constraint of space. So light's dumb. It doesn't have any knowledge whatsoever, right? It doesn't have any idea.
Some light.
It's dumb old light. So
Yeah.
it just follows the curvature of space. So that said, that's what we can say. Okay, is that light follows the curvature of space, and if it's enough curvature in there, light will just keep going around and around and around and never get out.
Right.
It's stuck inside the curvature of space, and that's what we mean when we say not even light can escape a black hole. That's what we mean. Now, Francis Palmer asks a great question.
Mm-hmm.
How can a black hole grow in size if it has a singularity at the center? Part of the black hole grows as the accretion disk that grows. I have a perfect answer for that. A black hole singularity, as defined, as we talked about, is just the center point mathematically that we talk about for the center of gravity. But the black hole has mass in it, and the black hole size grows based on how much mass it has in it. And we calculate that size of the black hole by calculating its Schwarzschild radius. The Schwarzschild radius is a radius that's defined by the mass of the black hole. And this tells us, as far as we understand, it tells us how big the black hole is going to be based on how massive it is. If you look up the Schwarzschild radius, you can easily find its calculation and do it yourself and see how big a black hole would be. Example, the black hole that is in Messier 87 looks like this. This is the black hole. Yeah, this is the black hole right there inside Messier 87. And this black hole that we're seeing right there is, tens of millions of light years away. And it was captured by the Event Horizon Telescope, which basically uses the entire Earth to get data for, its telescope. It's a bunch of separate telescopes that add their data together. And this is what we got. We can actually see the black hole in the middle. That's sort of like the shadow of the black hole. This is a radio image, by the way. So the bright spots is stuff coming toward us. The red spots is stuff going away from us.
Okay.
Yeah. So that's what that means. And so when we look at a black hole image like this, no matter which way we look at a black hole, it's going to kind of look like this. And you might say, but wait, what if it's at a different angle? And wait, Mark, don't black holes have these accretion disks around them?
Yep.
Yes, they do. And I just so happen to have a black hole model. So this is a black hole, and this is the accretion disk around it, okay? Now, when we see, first of all, what's an accretion disk? An accretion disk is a disk around any object. The solar system was made from an accretion disk around the sun when it formed. An accretion disk is a normal consequence in the universe, and it comes from material coming in from all sides initially, but it ends up tending to be one path. All right. And it has to do with studies of angular momentum and stuff like that. But take it for granted that what I'm telling you is true. It will tend to form a ring, a disk around an object. And so that's what we're seeing here. This accretion disk is a ring of material, a disk of material that forms around the black hole. Now, as this stuff is going around, you can understand the black hole is a very powerful gravitational field. Okay. Well, what if it's like this, an edge to us? Well, how could we see this almost everywhere we look? That doesn't make any sense.
Mm-mm.
Well, it kind of does, because watch this. If you look at a black hole and you see that there's a disk on the other side, like here, keep in mind that this thing is bending space. So the light from the far side of the disk is going to be coming up off the disk and bending toward the black hole and then continuing on its way, right? It's going to come up and go on. So what you see as a result of that is it looks like the light is coming from above the black hole because it's going to bend and come now toward you. This is the light you see. So you see a shape that looks like this. This is how a black hole will look for you here.
But isn't the other side bending and going the other direction then?
Well, this
doing
one,
the same thing the other direction?
No, because this is on our side of the black hole. This is on our side of the black hole,
so we don't see that bend.
We don't. No, it's if you're on the other side, then yes, some of its light would be bent. But we're on this side. We're seeing the light here, okay, coming to us. The light from the other side of the black hole is what's bent. So wherever you're looking from, you spin it around. The other side is going to look like that. So the side we just looked at is going to also do that. Okay. So it's just the stuff near the proximity and beyond the black hole that's going to change and look like this to us. Okay. And this is why when people draw images of black holes, we now do this. Right. You're seeing the accretion disk on the near side in the foreground there. And then you're seeing the other side of the accretion disk being bent over the top.
Wow, I never realized that. I always thought it was because everything was coming in at one angle and it was just a way to represent that image. So very cool.
So you see gravity does its work, doesn't it?
Very cool.
Gravity does its work.
And is it the strongest thing in the universe?
Well, in terms of forces, no. Gravity is actually the weakest, believe it or not. The strongest is called the strong nuclear force. It's what holds protons together. And when you have if you have protons, you have a material inside the protons. There's 3 particles inside a proton called quarks, and these quarks hold together. You have 2 up quarks are called, and 1 down quark that makes a positive 1 charge on the proton. 2 down and 1 up, opposite. Gives you a 0 charge to give you a neutron. Yeah. So I know that sounds kind of wacky, and I'd have to explain it and show you. But
that helps.
Yeah, it is cool.
Mm-hmm. Did you see what Ron said? If you squint, it looks like a UFO. Did you see that? The black hole. It did. It had the shape of a saucer, sort of.
Yeah, that's correct. And I do have a theory about how flying saucers operate, and I do believe that they operate by using massive amounts of gravity. So yes, and so you would see a pronounced effect on the craft, by gravity. So this is something that I've been doing this talk all over the country, and people really find it fascinating. And so I think it's really important to understand that this is the kind of thing that we're moving into with science, is the understanding of not only how gravity works, but an understanding of how any potential visitors to our planet can use gravity to get here. Real quick on the black hole thing, when we look at a black hole, the area beyond which light goes into that forever circular, circle path and doesn't come back out, that's called the event horizon.
Right.
So at that junction at a black hole's location, that's where it has warped the fabric of space so much that light that enters just beyond that radius from the center is now only going to go wee and be stuck in there forever. Now, I thought it's kind of a romantic thought that maybe space is dark because we've been inside a massive black hole, and that's our universe, and that kind of a thought. But I will say this. Black holes can be pretty large, and that black hole that I just showed you, this guy right here, right, that one right there is in the constellation Virgo in Messier 87, the Virgo galaxy. That black hole diameter is literally 5 to 6 times the size of our solar system.
Oh my gosh, that's huge.
And it took us 10 years to get to Pluto.
I was gonna say that includes Pluto, right? The
I include
planet.
Pluto.
Yes.
Yeah, 5 to 6 times the size of the distance from Earth to Pluto. Can you
Wow.
imagine that? A black hole. That's huge. That's absolutely stunningly huge. So they can be large, and a lot of the people that were talking in chat about black holes, hopefully you can see. Hopefully you can see what I'm talking about. Then, when I talk about this thing called a singularity, it's a mathematical convenience. It's not an actual point, because then from the singularity outward to the event horizon, what's all there? Well, it's
Would it
pulling in
be
mass.
really if you were inside the black hole, which that we could never do this, but do they imagine that it would be really bright inside a black hole, even though it's dark from our perspective, but inside it has all that energy going on? And would it just be like the sun is bright because of all the energy and stuff
Well,
like
there's a construct, Tara, since you mentioned it. There's an interesting construct that if you have a black hole, then maybe there is a complementary white hole
that? I've never
where
heard of that.
material streams out. None's ever been found, but is it possible? Maybe.
Huh.
I sat with the guy. He was a consultant on Interstellar.
Ooh, cool.
The astrophysicist consultant. I don't know why I can't think of his name right now. I'm sorry, because I feel like I'm insulting him now. But he and I sat for 3 hours talking about black holes. And when we did, he talked about how if a ship went into a black hole, as it was entering the black hole, right, several things happen. First of all, you get to the point where the ship's light would not be able to come out to reach you as it moved further in. So it'd go to a certain point, and then on the surface of the black hole, you'd see the ship forever and ever. Meanwhile, it's gone way inside, but the
Weird.
light that was coming from it was only seen to the point where the light could escape. And after that, it's not going to be seen anymore.
Weird.
So it would just
Yeah, makes
appear there forever because it'd be hung. It's being pulled in, but not, you know what I mean? It's following the curve. So that's
So the
one
whole
thing.
surface would be full of those images.
Effectively, at any one time, yeah, but it is a
Mhm.
black hole after all. So
Yeah.
they're not white.
Yeah.
So obviously that doesn't last forever. So the thing that's interesting is he said that if you could do some type of entry into a black hole, as you're about to enter the black hole, if there was a complementary white hole next to it, and it was the complementary one to this black hole, as you were starting to enter the black hole, you'd see your ship coming out of the white hole before you went into this black hole. Now, wait a minute. Exactly.
What?
Yeah. It's not time travel. It's information time travel. It's time travel of information. So it's kind of weird how that happens. And it's this a magic moment where it'll happen just before you get spaghettified and crushed to death.
So there's not enough time to tell anyone what you just saw.
No.
No. Yeah, okay. Turn it.
Yeah, I know, right? So yes, that's pretty cool.
Very cool.
Yeah. So now, as we talked about, the space-time curvature that's induced by a big black hole. Again, massive objects like stars and so forth will warp the fabric of space-time. Our sun warps the fabric of space-time. In fact, one of the proofs of relativity is actually to look at the sun during an eclipse and measure the stars, and notice that the stars have been warped behind the sun. They've been warped. So because the sun's gravity is enough to kind of warp the light a little bit. Because the sun is what we call a gravity well. It's got a well of gravity. Earth has a gravity well. The moon has a gravity well. I have a gravity well. You have a gravity well.
Okay.
It's just small. Okay. And if you were to draw a gravity well on your Etch a Sketch, you probably would draw it as a little well.
Okay, I'll do that next time. Yeah.
I see it right behind you there.
That's my UFO drawn on that one. Yeah.
Cool. You can show us if you want. So space-time curvature is a phenomenon that's caused only by these black holes, and the curvature can be quite dramatic, as we said, and the curvature can be so dramatic that you might not be able to get light to be able to escape again. And that's the whole point. And that's why they say that. Again, keep in mind, light has no mass. And we think of mass as being affected by gravity. But gravity affects the space-time curvature, the fabric of space. So light follows space.
So
And because it does, it will follow the curve.
I'm sorry.
No, go ahead.
If light has no mass, so is it information traveling as well? Like you kind of mentioned just a bit ago, is that an information?
Well, I mean, the information we could get from light traveling, I mean, the spectrum of the light is going to be whatever it is, the photon. Okay, the energy of the photon, the frequency of the photon. That's information that we would track on a photon.
Right.
And so as it got into the black hole, it'd get to a point where it could no longer escape if it passed the event horizon. And the event horizon is defined as the Schwarzschild radius of the black hole, or by the Schwarzschild radius. So that's kind of the weird thing about these things, So it's interesting too. Okay, there's a lot of paradoxes with black holes. One's called the information paradox. Okay, we also have interesting outcomes of a black hole. We have we have things like the concept that the black hole is not completely black. They do emit radiation, and all black holes evaporate. I don't know if you knew that, but black holes do evaporate
over time, long time, right?
Well, actually, micro black holes, which exist as theory and potentially, they would last a few nanoseconds, and they would evaporate in that amount of time.
Okay.
Right? A black hole that's the size of, I don't know, our sun might take millions of years to evaporate.
Yeah.
So I don't think that they do evaporate, but they evaporate slowly. And the reason is they're giving off energy, and anything that's giving off energy is losing data. It's losing information to us, and something is happening. If we're getting light coming out from this black hole, it's going to evaporate as it starts to leak its radiation away. Well, it's coming from somewhere, and sooner or later, all that radiation is going to be gone.
Yeah.
And the black hole will be gone. See?
So the red stars are the ones that blow up first, correct? Is that
when they're giants? Okay,
and they're giants? Okay.
Yeah. See, the thing that's interesting, and we gotta look at this. We gotta look at this diagram again. This diagram, okay, at the upper left, you see the blue hot stars, and you see that snaky line that goes down to the red stars at the bottom.
Yeah.
Okay, these are the main sequence stars. These are the stars that fuse hydrogen into helium normally. Okay, the confusion comes because when you see a red star in the sky, you don't know if it's one of these ones at the lower right or one of these giant ones at the top.
Oh, okay.
Yeah.
Mm-hmm.
Now, these ones that are giant near the top and midway to the top, those stars are actually much more massive than our sun. And so when you see stars that are much more massive, those are the stars that could end up being supernovae. All right. Stars that are on the main sequence, that main strip there, those are not in danger of supernovae, although someday they might be. Okay. But the ones that tend to be at the lower right end, those are M-type stars. But you see, the star's designation and classification is based on two quantities. One is basically the color of the star. You have the OBAFGKM along the bottom, which corresponds to a certain temperature range for the stars. Okay. And it goes from say 30 to 35,000 Kelvin on the left to 3,000 Kelvin on the right. And that's a temperature scale. So it's a little bit more in Celsius and a little bit more, a lot more in Fahrenheit. So that said, these stars are extremely hot, right? And if you look on the left scale, and it's not color, you have a 1. You see that 1 right? I should point to it right there.
Yeah.
See it?
I do.
That's 1 solar luminosity. Okay. And that, if you draw a line across, you'll see the sun is right there in the middle.
Okay.
Okay. Now, there are stars that are 1,000,000 times more luminous than our sun. And that luminous star will end up being a lot more massive, maybe 60 times the mass of our sun. Okay. And sometimes these stars are going to be, using up their hydrogen. Well, they will all be at that scale, at that upper left scale. They'll use up their hydrogen very, very quickly, and they will quickly migrate off of this snaky main sequence line and become a supergiant in the upper right that you see there.
Mm-hmm.
And those supergiants are the ones that will become supernovae in short order. And short order can be just like, within just a couple million years of being formed as a star. Now you see on the upper part there, on the upper left, you can see that at the 60 and 30 mass star, there's like a blue smudge that travels over into the supergiant realm.
Mm-hmm.
That's the general path that these stars will take. And they go to become these supergiants. And then as they get even bigger, they'll get cooler on their outer fringes because they're farther and farther away from that inner core. All right. And then they will turn redder. So Betelgeuse probably started its life as one of these hot blue O stars at the upper left of the diagram here. Now it's at the upper right at that end. So I got to go backwards here. At the upper right there, okay, and way at the upper right, you see it says Betelgeuse there. That is where Betelgeuse is now. And so it's migrated off because it stopped fusing hydrogen into helium very quickly, probably within 1,000,000 or 2 years. And then it started burning helium into the nitrogen isotopes, and then carbon. And then the carbon went into oxygen and so forth, and making its way down the periodic table as far as potentially iron. And so Betelgeuse is at that point where it's probably within 1,000 to 10,000 years of going supernova. And so when it goes, it's going to really blast big time. And it'll be so bright that we'll see it in the daytime.
I hope we get to see it. That would be amazing.
I know. I hope we're all wrong about it.
Yeah. So the first black holes then were created from those types of stars then? Like Betelgeuse, do you think?
Yeah. I mean, the other thing, that's actually a very good question. Like the origins of black holes. Okay. We know that they come from massive stars. We also know that black holes, there are some that are primordial. They were here when the universe began, formed by the beginning of the universe. And primordial black holes, again, are not formed the same way as the black holes we're talking about. But primordial black holes are black holes that, like I said, might have been here initially. And there's probably a fairly good number of them out there.
Wow.
And it seems like there is. We've seen evidence that these things might be out there.
Mark, are they in that timeline of the universe where you kind of get some of those pictures? Do they mostly exist in the early part of the history of the universe that we know of, or?
Well, they would actually the black holes we're taking pictures of. Yeah, that's okay. But correct me if I'm taking your question the wrong way.
No, go ahead.
If you look at the beginning of the universe, there's a number of black holes that have that were around from day one, and those black holes may have been massive and not evaporated yet. So there might be some out there, and as far as the black holes that we see, we can link most of the black holes we see to a supernova remnant like this one, okay? Or like this one, okay? This is a supernova remnant. It is, isn't it? Okay. And again, these are all pictures we took with our telescope for Sky Tour. And so when you look at supernovae like that, we can link them to a black hole that may have been left behind, okay, or a neutron star that was left behind, right? So we can typically link them to something we think that might have been caused them. As far as primordial black holes, they may be just floating in space. And so finding them would be like a happenstance of looking for a gravitational lens and saying,
Oh.
hey, what is that? That must be a black hole or something causing this gravitational lens. You know, as far as I've studied primordial black holes, so I don't know. You know, I always thought of it was a very esoteric subject. And I actually had a lot of trouble believing they actually existed, to be honest with you. But I can see the physics of how they can occur. And that's the thing that makes the most sense to me. You know, the white dwarfs, the electrons are powerful enough to hold the white dwarf up. But if you squeeze even more mass, it gets heavier, more massive. And now it wants to collapse even more. Now the protons and electrons are squished together effectively to make neutrons. Okay. And that process is something that would make a neutron star. Squeeze the neutrons together even more. And now you're squeezing them into a gravity well that will keep light from escaping. And that's what we call the black hole. See? So we can't get in there to see. So we don't know what's really going on inside. Like I said, it'd be kind of funny if we could find out someday that our entire universe that we show you in real time with SkyTour live stream is a view from inside a giant black hole.
Wow, wouldn't that be amazing?
It wouldn't help us, but you know, and also another thing too I thought of was that maybe the universe is a gigantic black box in someone's living room. Right?
Mm-hmm.
How do we know it's not true, right? We can say, well, that's a silly concept. Is it?
Some people think it's a hologram or something like that, or
yeah, I mean, and you know something, we have data to suggest it's really there and real distances that we can measure. So I trust those measurements. So I'm not a universe is a hologram guy, or the moon is a hologram guy. And that's fine. But I will tell you this: these findings that are coming out, there's a lot more to it than we realize, and there's a lot more to the universe than we have known. And one of the things that, and this will be I might actually do this talk for you next time. There's some particles that you could use to generate micro black holes around a spacecraft. And if you could generate micro black holes around a spacecraft, these particular particles would actually drag you out of our 4 dimensions moving through time. X, Y, Z moving through time, 4 dimensions, and pull you into a 5th dimension. And that 5th dimension is an area where the universe is warped, highly warped, and the farther in you go, the universe is compressed around you, much smaller and smaller and smaller the farther in you go. So if you go in a moderate amount, you could pop out 2 light years from where you are and not have traveled the intervening space between here and there. And that's the process that I've been talking about lately, the Kaluza-Klein particle hypothesis, the Kaluza-Klein graviton process. Now, what's interesting about this process, and when I do the talk a few, like next week or whatever, you'll see it in intricate detail. The thing about this process that makes it really interesting is that this is something that can explain every observation ever made of a UFO.
Huh?
Yeah. This is something that can explain every location a UFO has ever been seen. Underwater, moving at very high speed and not disturbing the water. In the air, making right-hand turns, at high speed. How the heck did it do that? All these things can be explained by the use of these particular particles. And what's interesting about it is that because to our eyes, we're seeing something shifting to a 5th dimension and back to our 4 dimensions very rapidly. So it's just doing this, very quickly. That's what it's doing. And it just goes in an oscillation back and forth very quickly. So it's neither here nor there. So it's not subject to the forces here and not subject to the forces there. It's sort of in the netherworld in between at all times. How could it do that? You might say, well, that sounds like woo-woo stuff. No, it's not. It's actually something that is possible if string theory can be proven right. And when we talk about it, I'll mention Randall Sundrum 1. It's a variation of string theory, RS1, Randall Sundrum 1. And basically that says that you have these 4 dimensions, and then you have this 5th dimension, okay, called the bulk, like bulk produce, BULK. And if the ship can go back and forth between these 4 dimensions and the 5th dimension rapidly enough, then you see, as far as the ship goes, to your eyes, you'll see the ship. And if it's going back and forth here and there, and every time it comes back here, it moves ahead 6 inches, you will see to your eye an object moving through the sky at high speed. Okay, maybe it goes 5 feet at a time, and it'll look like something going zam, like thousands of miles an hour through the sky, not even making a sonic boom. Now, if that happens, now what if you see it and then it goes ding ding and it makes a 90-degree turn? Whoa, how did that happen? And didn't the occupants get like smashed against the wall of the spacecraft?
A few G forces, yeah.
Yeah, you would think. No, they don't feel a thing. It feels like everybody listening sitting in the rooms right now. Okay, because they're using a dimensional shift capability. They're shifting back and forth. And that's all they're doing. They're not physically moving. They're just shifting to that 5th dimension and then coming back to the 4th dimension at another entry point. So they're just stepping out and stepping in. They're going out, in, out, in, out, in. And when they come back in, they're just, 5 feet further from where they were last time. So that means that they're not going to feel any inertial forces at all on them. Okay? They're not going to disturb the air. They're not going to cause anything underwater. They're going to be able to be underwater, then shift into the 5th dimension, the bulk, and keep coming back and forth, 5th, 4, 5th to 4, and just keep shifting back and forth. They might say, it sounds like a lot of work, but here's the benefits. They don't need engines. There's no fuel tanks. They just have to generate these particles. And when you look at these objects, when you look at these craft, okay, haven't you noticed that there's the flying saucer? Remember this guy? Okay, why are they saucer shaped? Why did that shape become a predominant shape? You know why? For the reason of the need to create these particles I'm talking about, the Kaluza-Klein gravitons. To make the gravitons, you know what you need? A particle accelerator. And what shape are our particle accelerators? They're rings. Okay, the Large Hadron Collider is a ring. Okay, these guys, I think the outer rings are particle accelerators, and the occupants are safely in the core. Okay, and what happens is they surround the ship with these Kaluza-Klein gravitons, which are very, very powerful, 10 to the 16th times more powerful than the gravitons holding us to our chairs. Again, assuming gravitons exist, we haven't found them yet. Okay, and those gravitons, all right, that are coming from the Earth to hold this UFO down to the ground are being absorbed by the Kaluza-Klein micro black holes, because when the Kaluza-Klein particles go around the ship, they're also creating these micro black holes. And those absorb the gravitons of the Earth, not allowing Earth gravity to reach them. Not, this guy, not to allow the Earth gravity to reach the ship. So it just sits there and flutters like a leaf because there's nothing reaching it. Okay. And so if they turn off the accelerator or they stop making these particles, they can sit down on the ground, and now they can come out and do some investigation, go back into the ship, start up the accelerator, move up to the, punch out from here, punch in here, go up higher altitude, whatever. And here's another thing that makes sense. Not only are these circular because they're probably particle accelerators, I think. Whenever you have reports of people getting near UFOs, what are the reports that what other features do they report?
Radiation type of thing?
Yes. They report radiation burns, right? Well, guess what? In a particle accelerator, when you're trying to force particles to go in a circular path, they are being forced into a circular path by a powerful magnetic field. And by doing that, forcing high energy particles in a circular path, they give off radiation, synchrotron radiation. Synchrotron radiation. Synchrotron, yes. Synchrotron. Synchrotron, yep. Synchroton, synchrotron. like sync, SYNCH. And synchrotron radiation is deadly to you and me. And if you are exposed to it, it will hurt you. You'll have radiation burns. Surprise, surprise. So that makes sense. Now, let's consider some of the other effects. When people look at UFOs, what do they say sometimes? They look like they were shimmering. They look like they were changing color. They seem to pop out and appear over here rapidly. And, why did that happen? Well, I can tell you astronomically reasons why that could be true. Okay. And I will in a moment. But consider this. When these black holes are surrounding the ship, they're not only absorbing the Earth gravitons, but they're absorbing some of the light that would normally get to you, aren't they? Because they're everywhere, right? Then they only last for a few nanoseconds and then they're gone. So the ship is generating a multitude of these and keeping a net supply of them around the ship. And they're going to make the UFO look like it's shimmering or like a mirage, fluttering in shape, might change color, okay? And so because these micro black holes are absorbing some of the light that's also coming to you from this UFO. So it's going to make the light look really odd and do some strange things. Okay. So when the ship actually looks like it's moving to one place and another in the sky really rapidly, it might only be popping out and popping in. So to them, they're here, then they're here, and then they're here. It doesn't have to be that they're going in all these directions, because we're assuming that it travels this distance to get to here. I don't think so.
Right.
I think it's just popping out of here, bink, and reappearing here, bink. So that's only 2 steps. It's not like the infinite number of transitions you go from here to here. I think it's because it's actually going, from here directly to here. Do not pass go. Do not collect $200. It's not actually creating a path. It's creating a set of discrete pops.
Is that kind of like quantum movement, or when you don't see the movement from here to here? Sometimes it's not really quantum movement, but I think like a bird's head. A bird can move his head so fast you don't see it. And
I know what you mean. And to our eyes, yes. See, the observation from our 4 dimensions is extremely important. So you're right about that. What we see in our 4 dimensions is the effect of a craft that's using 5th dimensional travel possibilities. And so this will look to us like magic, right? I liken it to this. Imagine going to ancient Babylon with an F-16 Fighting Falcon fighter plane. Yeah, zip over everybody.
Whoa.
You will be a god.
Mm-hmm.
Okay. Now, the thing is, people say, well, if they're so advanced, if aliens are so advanced, why do they crash? Well, let's again do that sliding scale of technology. If you're in ancient Babylon and you're F-16, that as advanced as it is, it can crash. And they do. What if it crashed in ancient Babylon? Yeah. The gods can be killed. Oh no. Or they would say, well, we managed to acquire Centurion. We managed to acquire, for ancient Romans, we managed to acquire this thing that crashed. That's weird. What is that? It's made of a material I've never seen before.
Kind of like we're doing now.
They couldn't make titanium back then. So if you think about it, an alien race being here, they might be more advanced, but they're fallible. They're not,
I agree.
They're not gods. They can crash. They can be killed.
Oh, I can't wait to hear more about this, Mark. So you're going to talk about it next week? Okay.
Yeah, I think we'll do it next week. Yeah. So I know we're coming to the close of today's show, and I do want to say to everybody, thank you for coming and being here. I know that we'll have a good time next week. So you guys enjoy yourself, and we will talk soon. And I'm looking forward to doing a stream very soon. Actually, we're going to get back at it real quick. So thanks, guys, and we'll talk to you again. Good night.
Hi, everyone. Thank you.
Mm-hmm.